Sony SNC-DH260 surveillance camera, which is a pretty expensive unit. I bought it for €9.38 as defect. New, it would cost almost €1,000. Here's what it looks like now that I've repaired it. It is capable of delivering full HD video. It has mechanical zoom and focus lenses. And you can get all sorts of great settings. So here's how I did it. I briefly disassembled the camera to see if there are any major defects that might cause the whole thing to explode on me when plugging it in. That was not the case, so I plugged it into this power over Ethernet power source. And as you can see, there are some LEDs coming on, which is a pretty good sign. But it will get even better in a moment, as you might be able to hear. That click was the infrared filter that was being moved away from the lens, as I found out later. Now, this is really great news. It actually displays something. It's just black and a whole lot of noise, but it's something, and I'm fairly confident now that I can repair this. When shining a bright light straight into the lens, I'm getting something like an underexposed picture, which tells me that the image sensor is still good, and it's probably just a problem with the mechanical aperture in front of the sensor. So I dug a little deeper this time and found a whole lot of water damage, especially on this tiny intermediate board that was mounted directly onto the camera assembly and kind of connected the main board with all the stepper motor drivers and so on. We have this infrared filter with just a 2-wired solenoid. Then this aperture kind of thing I've talked about earlier. It is normally closed and driven by 2 tiny counteracting motors. That way it can be driven with a standard cheap stereo power amplifier IC. Then there are 2 standard 2-phase stepper motors for zoom and focus, and Opto Interrupters as limit switches. I also had some problems with these so-called Opto Interrupters. One of them had a defect output opto transistor. It was basically just a dead short. What these do is tell the device when one of the lenses is in their end position. What I'm using now are these Omron EESX113 and with some minor adjustments they work just fine. I cleaned it up and started to test continuity, only to find out that there are many open connections. So presumably some internal layers were just rotted away. I ended up bridging the connections that were routed through this board. What was left afterwards were first this wire with a PWM duty cycle inversely proportional to the brightness of the image. Secondly, a ground connection, and third, a 5-volt array connection. So obviously the few parts on the tiny PCB are a constant current source for the infrared LED ring. Since I had no trust at all left for this board, I wanted to rebuild it completely, but I couldn't find out what IC it was based on, so this part turned out to be the most difficult. I thought about ordering this ridiculously expensive step-up converter and just making 12 volts out of the 5 volts and then just chopping it up based on the PWM signal with a big MOSFET. That would probably work, but be pretty expensive. So I thought, yeah, I should be able to find just the right IC. I googled what I need. A constant current source with a boost converter and PWM input. And sure enough, the fifth result seems to be just the right thing. LM3410. After about 1 week of playing around with this LM3410 constant current source, I finally managed to get a working prototype. Turns out this is a pretty delicate device, mainly because of its high PWM output frequency. It is pretty difficult to get a PCB made that fulfills all the design rules of Texas Instruments that are given in the datasheet. I'll talk about that later. Cover the lens. It soon goes to night mode. I've got the camera output there on the PC screen and it's black right now. It will soon pop the IR filter in front of the lens, then do an autofocus, and then turn on the LEDs. There comes the infrared filter. And here come the LEDs. Here's the PCB design I finally made after killing about 5 of those LM3410s, because as I said, they are very fragile. So the most important parts are these 2 capacitors. Those must be put as close as possible to the device itself and the ground plane below it. Then I made these huge pads to be able to try out some larger inductors later. I tried using these very small ones, 100 microfarads, but seems like they are too small. Then here's another important portion that I wish I had used much earlier. That is an overvoltage protection. And as you can see, they are not giving you the advice to use that in the typical application in the datasheet, which is kind of bad, I think, because I killed, as I said, 5 of these constant current sources because I didn't have that overvoltage protection. It is stated right here that it's possible to use that, but I think it would be better to have them in all the example applications down here. Because even though this is a pretty clever device with over temperature thermal shutdown, it has no overvoltage protection, which means if you, for example, put on these LEDs backwards or put on no LEDs at all and turn the device on, the constant current source will think that the current through the LEDs has dropped, and so it will increase the voltage over the LEDs more and more until failure because of overvoltage. After all I've been through, I think you're better off following as many of the design advice from the datasheet as possible, especially if you're using the higher frequency model.